Welcome to qnawire.
Hi, so we are given a combination of 4 capacitors. So let me first draw the combination which is given to us. So we have these 4 capacitors. Capacitor C1 is 3 microfarad. Let's call this C2. Capacitor C2 is 6 microfarad. Let's call this one C3, which is given to be 6 microfarad. And we have the capacitor, the 4th capacitor, as 3 microfarad. So we are given these 4 capacitors, which are connected like this. We have the points A, B, this is C, and this is defined to be D. So we have these 4 capacitors C1, C2, C3, and C4 connected in this combination. So it's given that the capacitors connected in this combination, they are initially uncharged, connected as shown with the switch as open. So initially the switch as is open. Then the applied potential difference between the points A and B. So the potential difference between A and B is applied to be plus 210 volts. So this is the given information. And in the first part of the problem, we need to find the potential between the points C and D. So we need to find, so for the first part, we need to find the potential between the points C and D, so VCD. So this is what we are required to find in the first part of the problem. Now, in order to solve this, we need to find the charges on each of the capacitor. So in order to find the potential between the points C and D, we got to find the charges on each of the capacitor. And as you can see, the 2 branches of the capacitor, when the switch is open, so when the switch is open, so we have these 2 branches of the capacitor. So this is one branch, and this is another branch where we have capacitors C1 and C2, and on another branch we have capacitors C3 and C4. So when the switch is open, as we can see, the 2 branches are identical because they have 2 capacitors each having same values, that is 3 microfarad and 6 microfarad connected in series. So the 2 branches, since they are identical, they are going to have same charges. This means that all the 4 capacitors, they're going to have same charges. Like if the branches have same charge and the capacitors in each branch is connected in series, and as we know, in series combination, the charge on each capacitor is same. So if this branch and the other branch has same charges, then the charge is going to be same on each of the capacitor, which is going to be half of the total or the equivalent charge of this combination. So let us first try to calculate the equivalent capacitance. So as we have seen, we have 2 branches. Like in each branch, we have 2 capacitors connected in series. So the equivalent capacitance. So if I want to find, let's say, the equivalent capacitance of this branch is C prime, and equivalent capacitance of this branch is C double prime, and these 2 branches are connected in parallel between the points A and B. So the equivalent capacitance is going to be C prime plus C double prime. But the equivalent capacitance of the two branches is going to be same. So because they have same combination of capacitors, 3 microfarad and 6 microfarad in series. So that's why it's going to be 2 times C prime, since C prime is equal to C double prime. Now, and as we can see, for calculating C prime, since C1 and C2 are connected in parallel, so I can calculate C prime like this. So C prime is going to be 1 divided by C1, so 3 microfarad, plus 1 divided by C2, which is 6 microfarad. And from this, I can very well calculate my C prime is going to be, so I have my C prime is going to be 2 microfarad. And from this, I can find the equivalent capacitance of this combination comes out to be 2 times C prime, which comes out to be 4 microfarad. So this is the equivalent capacitance of the given combination. Now, having found the equivalent capacitance, we can find, so this is the capacitance between points A and B. And we already know the potential between the points A and B. So we can calculate the total charge of this circuit. Q equals V times C. So we have V AB times the net capacitance. The VAB is 210 volts. So as you can see, so we have to be little bit careful here. So we have calculated the equivalent capacitance, which is 4 microfarad here. And now we need to calculate the capacitance in each branch. So the capacitance in each branch will be half of the total capacitance. So let's calculate the total capacitance. So total capacitance is going to be VAB, which is 210 volts here. 210 times the net capacitance, which is 4 microfarad. So I have 4 times 10 raised to negative 6. So 210 times 4 times 10 raised to negative 6. And this value comes out to be around 8.4 times 10 raised to negative 4 coulomb. So this is the net capacitance across A and B. And if you want to find the capacitance in each branch, so the net capacitance, it divides like this. So we have capacitance in the first branch, the upper branch, Q prime, plus the capacitance in the lower branch, Q double prime, charge. So the charge is going to divide, because the net charge is going to divide here like this in two branches. And as we have already seen, since the combination of capacitors in two branches is same, so the charge in each of the branch is going to be same. So Q prime plus Q double prime is indeed going to be equal to twice Q prime. And if I want to find the charge in each of the branches, so it's going to be Q prime equals total charge divided by 2. And if I find this, so it's going to be 4.2 . times 10 raised to -4 coulomb. So this is the charge in each branch, or I can say this is the charge on each of the capacitors. Now, having found the charge on each of the capacitors, I can find the voltage at point C. So voltage at point C is going to be, as you can see, the voltage at point C is going to be the voltage between A and B, VAB, minus the voltage across the 6 microfarad capacitor. So this is going to be equal to 210, which is the voltage across VAB, minus the voltage across the 6 microfarad capacitor here, this one, and the voltage across 6 microfarad capacitor is V equals Q/C. So the charge across each 6 microfarad capacitor is 4.2 times 10 raised to -4 divided by 6 microfarad. So 6 times 10 raised to -6, and this value comes out to be around 140 volts. Now we have found the voltage at point C, VC. Similarly, we find the voltage at point D. So the voltage at point D is again going to be, so we have the voltage between the points V, A, B. So voltage between the points V, A, B minus the voltage across the capacitor C1, which is 3 microfarad. So this basically comes from the point that since it's a parallel combination, so the voltage across C1 and C2, the total voltage across C1 and C2 is going to be VAB, which gets divided. So it comes from this. Since total voltage VAB is going to get divided in between the points VC1 plus VC2. So VAB, as we have already seen, equals 210 minus voltage across C1. So voltage across C1 is charge divided by the capacitance. So charge is the same, 4.2 times 10 raised to -4, 2 times 10 raised to -4 divided by the capacitance itself. So it's 3 times 10 raised to -6. And if we calculate this, so this value comes out to be around 70 volts. So we have calculated voltage across at point D and voltage at point C. And we need to calculate V CD, which is going to be equal to VC minus VD, which is, so voltage at point C was 140 volt and voltage at point D is 70. So 140 minus 70, which comes out to be 70 volt. So this is the final answer. So this is the voltage across point C and D, VCD. So this was the first part of the problem. Now in the second part of the problem, we need to find what is the potential difference across each capacitor after switch S is closed. So we need to find the potential difference across each of the capacitor when the switch is closed. Now let's go back to the figure. So initially the switch was open. Now when the switch is closed, every 3/6 combination of capacitor are together in parallel. Now if you so if you see like when the switch is closed, when you close the switch, so you'll see that the combination of capacitors C1 and C3 and C2 and C4, 3 and 6 and 3 and 6. Oh no, not that. Like sorry about that. So when the switch is closed, when we close the switch, so as you can, so initially 3 and 6, so C1 and C2 were in series. So when the switch closes, C1 and C2 will be in parallel and C3 and C4 will be in parallel. Yeah, so yeah, that's right. So when the switch is closed, C1 and C2 and C3 and C4 are in parallel, and the two combinations together are in series. So this C1 and C3, they are in parallel, which is in series combination with C2 and C4. So if I want to draw it here like this, so when I close the switch, so this was C1, C2, C3, C4. When I close the switch, as you can see, C1 and C3 are in parallel and C2 and C4 are in parallel, and this two combination is in series. So this is what I was saying. And so this was my point A and point B. So we know the potential between points A and B. So the potential between point A and B is 210 volts. And since C1 and C2, as can be seen, C1 is 3 microfarad, C1 and C3 is 3 microfarad and 6 microfarad, and again we have a combination of 3 and 6 microfarad. Since these two combinations, they have same set of capacitors, so 3 and 6. So by symmetry we can see when the voltage, if the total voltage between the points VAB is going to be 210 volt, so this voltage gets divided into two. So we have V prime and V prime, V double prime. So V prime is the voltage across this branch, and then V double prime is the voltage across this branch. And since the two capacitors like C1 and C3 and C2 and C4, they have same set of capacitors. So from symmetry, we can say that in each branch, so V prime is indeed going to be equal to V double prime, which is going to be equal to half of the net capacitance between A and B. So the net capacitance is 210 divided by 2, that becomes 105 volt. So across, so for this branch, we have 105 volt, and for this branch we have 105 volt. And since C1 and C3 are connected in parallel, so the voltage is going to be same across each one, C1 and C3. Again, C2 and C4 are connected in parallel, so the voltage is going to be same, that is 105 volt. So across each capacitor, the voltage indeed is going to be equal to 105 volt. And this is the answer for the second part of the problem. And finally, in the third part of the problem, we are being asked how much charge flows through the switch when it was closed. So from this figure, we need to find the charge flowing through this part of the circuit through the switch. So how much charge flows to the switch when it was closed? So we can see that the charge that flows to the switch is just the difference between the charge on the third on 3 and on capacitor 3 microfarad and 6 microfarad. So as you can see, C1 is 3 microfarad and C2 is 6 microfarad. So the charge which flows through this part of the circuit is nothing but the difference between the charge which flows across C1 and C2. So the charge that flows across 3 microfarad capacitor is, so charge Q equals V times C potential across V times the 3 microfarad capacitor. So we have the potential across the 3 microfarad capacitor. We already found it's going to be 1 of 5 volt times the capacitance, which is 3 times 10 raised to negative 6. And this charge comes out to be 3.15 times 10 raised to negative 4 coulomb. And then the charge across the capacitor 6 microfarad, again V times the capacitance across the 6 microfarad. So the charge across 6 microfarad is again 1 of 5 volt times the capacitance of the 6 microfarad. So 6 times 10 raised to negative 6. And this comes out to be 6.3 times 10 raised to negative 4 coulomb. And since the charge across the switch is just the difference of this charge across 6 microfarad and 3 microfarad capacitor. So from this diagram, as you can see very clearly, the charge across C1 is, which is, so charge across C1 3 microfarad and charge across C2 which is 6 microfarad. If you take the difference between these two, you'll get the charge across this part of the circuit. This is what we are doing here. And if you take the difference, the charge across the part of the circuit where we have switch comes out to be 3.15 times 10 raised to negative 4 coulomb. This is negative 4. And this is the answer for part C of the problem. This will finish this problem.